Alright guys, we're going to go through these notes on relations and functions. At your own pace, I want you to make sure you get all of this filled out, and I will hopefully be back on Thursday to answer any questions we have regarding the notes. Looking here, a blank is any set of ordered pairs. This is a relation. A relation. The next one says the blank is the set of all the first elements of the ordered pairs, or all of the x values. We have already learned about that. We know that this is the domain. And the blank is the set of all the second elements of the ordered pairs, or all of the y values. We call that the range. And relations again, can be represented in different ways. The first way to represent them would be in ordered pairs. So we have something like -1, 2, 0, -2, and 3, 3. We can also represent this, a set of data like this, in an XY table, or an input-output table, or a domain range table. Looking here, I have -1 goes with 2, 0 created -2, and 3 gave me 3. We can also use what is called mapping. In mapping, when we put our x's here and our y's here, we're going to order them from least to greatest. So the x's are -1, 0, 3, and the y's would be -2, 2, 3. And then to finish off the mapping, we are going to go from the x to the matching y. So -1 with 2, 0 with -2, and 3 with 3. And then, of course, we can also just have it shown as a graph. So I've plotted each coordinate, -1, 2, 0, -2, and 3, 3. These are some practice problems for you to go over. Go ahead and pause the video and work through all 3 of these, and then come back to check them. All right, hopefully you have worked through all 3 of these examples. I will go over the answers very quickly. For the domain of number 1, we are looking at 1, 2, 3, and 4. And for the range, we are looking at 3 and 4. 3 and 4 are repeated in the range. That's okay. We're just going to write them one time each. Now looking over here at number 2, for the domain, I have -1, 2, and 3. And for the range, I have 2, 4, 6. Now, if I were to rewrite number 2 as ordered pairs, we notice that there are only 3 numbers here and 3 numbers here, but we actually have 4 points. We have -1, 2, 2, 2, 2, 4, and 3, 6. So if we look, when we map, if we use a number more than once on either side, we would end up with multiple arrows going to a number, to that number. A set of multiple arrows going to that number. In this case, we have multiple arrows coming from 2 in the x value, going to 2 and 4 in the y's. Now we're looking here, and it's sometimes easier if we look at our points and plot them. So I have 1, 1. I have 1, 2. I have 2, 1. 2, 2, and 3, 3. So when I look at my domain, I have 1, 2, and 3. When I look at my range, I also have 1, 2, and 3. And although all of those except for the 3s are being used twice, I only write them once in each set. So looking here, we have a discrete graph, and that is a graph whose points are not connected. And a continuous graph is a graph whose points are connected. And so when we look at this first one, this first example right here, we notice that there is a line connecting this dot. I do not have to pick my pen up at all to follow that line. That line was already there. That makes this a continuous graph. And then if we look over here, each of these points are not connected by any line. That makes this one a discrete graph. And now looking at a picture, we can also identify the domain and range by just looking at a graph. This one starts all the way over at -1, -2. Right here, -2 for the domain. Now I'm going to write this one as an inequality. It's x such that -2 is less than or equal to x, and then the furthest x over would be at 1, 2, so less than or equal to +2. And then I'm going to do the same thing for the range, finding where that lowest point is. It's at -1. So I'm going to say that y such that -1 is less than or equal to y is less than or equal to, and then I have to see how high up I am. 1, 2, 3, 4. +4 up. Looking at this next graph, we notice the arrows here and here. That means that this is going to continue going all the way to the left infinity and all the way to the right infinity, which means that our domain of left and right would be all real numbers. And then our range, we notice it does not go below this point. So our range has a lower limit. So y such that y has to be at -2 or greater. So y is greater than or equal to -2. Looking here, we have a function. What is a function? A function is a relation in which each element in the domain is paired with exactly one element in the range. And what this means is that the domain cannot repeat. So looking here, we're looking only at the domain to see if we have a function. 0, -2, 4. There is no repeating number in those x values, so this is a function. If we look at t, I have 1, 2, 1. 1 is a repeating domain, so this is not a function. So looking here, we're just going over a few more of these to try and answer these as you can. We'll work on them together slowly. So it says, is the relation a function? And if we notice, we're looking for arrows twice, an arrow going twice from one number. 1 only has 1, 6 only has 1 spot, but 8 is used twice. 8 is used twice, that means it is not a function. When we look over here, 4 goes to -8, 6 goes to 6, -9 goes to 6, and 10 goes to 1. Now we notice that the two of them go to 6, but there are no double lines on the domain. As long as there are no double lines on the domain, it is a function. So we can look at this in table form or tabular form. Which relation is a function? We're looking for repeating numbers up here. -2, 3, 4, -2, -2, and -2 repeat. So this is not a function. Over here we have -1, 2, 5, -3. There are no repeats. This is a function. So looking here, it says consider a relation represented in graphical form. We have a discrete graph, not below, but to the right. Looking at this graph to the right, we're going to call this the set of T. And T includes 1, 2, 3 points. 1 here, 1 here, and 1 here. This is at 1, -1. This is at 1, 4. And at 2, 3. Those are our 3 points in our set. We are going to write those right over here where it says T equals, and it is 1, -1, 1, 4, and 2, 3. And now that's, is T is or is not a function? We see that 1 repeats in the domain, so this is not a function. And for relations represented as graphs, we can try this test. It's called the vertical line test. And it says that if any vertical lines pass through no more than 1 point of the graph of a relation, the relation is a function. So looking here, if I draw a bunch of vertical lines, only 1 point, 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 that means that this had no repeating x values, so this is a function. When I try the vertical line test, right off the bat, I see that it hits twice. This is not a function. And on this last one, try a couple. I only hit at 1 point for each vertical line test. That means that this is a function. Looking at these, I want you guys to try these 3 on your own. It says identify each graph as discrete or continuous. So pause the video and give these a try. Okay, looking here, these points are not connected. Not connected means discrete. Looking at B, we have a circle, which means that the shape has to be connected all the way through. That means that it is continuous. And on this last one here, our lines connect. That makes it continuous. Now, something that we're going to talk about right here is called function notation. And we can rewrite each one of these equations right here in function notation. We're just going to change one part. We're going to make each one of them look a little bit different. Function notation says f of x equals 3x plus 1. G of x, now it doesn't matter what number I use in front of the x. That's just a marker to show that these two are different, that f of x is different than g of x. 4 minus 2x. And h of x equals x squared plus 3x minus 6. And the expression f parentheses x is read f of x. And it represents the variable y. So f of 3 represents the y value for the function f when x equals 3. So let's try a couple of those together to make a little more sense of this. So we have f of x equals 3x plus 1, and h of x equals x squared plus 3x minus 6. It says find the value of each of the following. Number 1 says f of negative 2. So we're going to use this formula right here, but wherever we see x, we're going to put in negative 2. So f of negative 2 equals 3 times negative 2 plus 1. So f of negative 2 equals negative 6 plus 1. So f of negative 2 equals negative 5. And so for the graph of f, when x equals negative 2, the y equals negative 5. And looking at h of negative 3, we are now going to use this formula, or this equation. So wherever I see x, I'm going to put negative 3. So h of negative 3 equals negative 3 squared plus 3 times negative 3 minus 6. Now those parentheses are important because when we put this into the calculator, I need those parentheses to end up with the correct numbers. So this says h of negative 3 equals negative 3 squared gives me a positive 9 plus 3 times negative 3 minus 6. H of negative 3 equals 9. Now when I do 3 times negative 3, I end up losing the addition. It becomes 9 minus 9 subtracted by 6. And now I'm going to keep my order of operations going. And I'm going to do 9 minus 9 first, which gives me 0 minus 6. I'm going to keep going over here. H of negative 3 equals 0 minus 6 gives me negative 6. So when x is negative 3, y equals negative 6. And now we're just looking at a couple of these with a graph involved instead. So this says the function at x equals 4. So f of 4 equals, and what I'm going to do is come down to this graph. and I'm going to find where x is 4. 1, 2, 3, 4. The point is right up here. Use a different color so we can see it a little better. 1, 2, 3, 4. The point is here. That is at 4, positive 3. So f of 4 is 3. And f of negative 2, 1, 2, is right up here at positive 2. And now this is asking, what kind of graph is this? The points are not connected, so it's a discrete graph. And when we look at the domain, my furthest point on my x values, I have points on my x here, 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 and here. So I have negative 2, negative 1, 1, 3, and 4. And my y values, I'm going to look at where my y values are. I have negative 1, 0, 2, and 3. So I have negative 1, 0, 2, 3. Looking over here at this next graph, it says g of negative 1. So I'm going to go to the next, I'm going to go to the x value of negative 1 and then find the graph. That's right here. That is the point. It is at negative 1, negative 2. So my graph was found at negative 2. Now if I do the same thing for negative 3, 1, 2, 3, I go down to the graph, and I know that the picture is just a little bit off, but we are going to pretend like it's not. That is at 1, 2, 3, 4, negative 4. And if we notice, this graph is entirely connected. There's no gap. So that makes this a continuous graph. Now looking at the domain, we notice that the graph stops right here at negative 1, 2, 3, 4, 5. Negative 5. So the domain is x such that x, now it stops at negative 5, and then it keeps going this way, getting bigger and bigger. So we're going to say that x is greater than or equal to negative 5. For the range, it stops down here and cannot go any further. That's at negative 4. So y such that y, and now it's getting bigger. If we look in this direction, it gets bigger and bigger to infinity. So we are going to say y is greater than or equal to negative 4. So when we're looking at equations and talking about how to write them in talk in function forms, for the equation y equals 3x plus 2, we say that y is written as a function of x, or that y is written in terms of x. And that means that x is called the independent variable. It is the one that changes the value of the y. It changes the value of the y. And y is called the dependent. Dependent variable, which means that it depends on the value of y. So for the equation a equals pi r squared, we say that a is written as a function of r. R would be the variable, the independent variable. So a is written in terms of r, which makes r the independent variable, and A, the dependent variable. So that is all we are going to do for today. You may continue using your computer, but you must stay school appropriate. Hopefully I will be back again tomorrow.